G'day all, Nerd 72 here. Hope you're well. Um, I don't know whether you're watching this as a video on YouTube or you're listening to it on Spotify, but whichever the case, welcome. Thank you for tuning in. Today, by the way, at the moment I'm only casting on Spotify. For some reason, I can't work out how to get it from Spotify to the other platforms. I think I need to get somebody's help with that. Friend of mine who's does um, podcasts might be able to help me. But when I actually am able to, it'll be available on other platforms as well as Spotify. Anyway, in this episode, we're going to be talking about the formation of the solar system and Earth. So, the formation of the solar system and Earth is a complex and fascinating process that spans billions of years. This detailed examination will explore the key stages and events that led to the creation of our solar system and the Earth as we know it today. The pre solar nebula was a vast, cold, and dark region of space within our Milky Way galaxy. It was not uniform, but rather a patchwork of gas and dust clouds with varying densities and compositions. The primary elements in the pre-solar nebula were hydrogen and helium, which are the most abundant elements in the universe, as we found out in the last episode. In addition to these, there were trace amounts of heavier elements, including carbon, oxygen, nitrogen, and various metals. The nebula contained microscopic dust grains composed of silicates and other minerals. Um, Sorry, I lost my place. These dust grains played a crucial role in the formation of solid objects in the solar system. Gravitational collapse and protostar formation. Gravitational collapse began when some external disturbance, such as a nearby supernova explosion or a shockwave from a passing star, caused the region of the pre-solar nebula to become gradually gravitationally unstable. This instability led to the initial collapse. Um, as the nebula contracted under the force of gravity, the material at the center of the collapsing region became denser and hotter. This central region, known as the core, was the future birthplace of our sun. As the core continued to contract, it underwent adiabatic compression, which means that gas particles within were squeezed closer together, raising their temperature. This process continued until the temperature and pressure in the core became high enough to initiate nuclear fusion. Nuclear fusion is the process by which hydrogen atoms in the core of the protostar combine to form helium, releasing an enormous amount of energy in the form of light and heat. This energy production marked the birth of the sun as a true star. Before the protostar fully stabilizes as a main sequence star like our sun, it goes through a phase called the T-Tauri phase. During this phase, the young star exhibits irregular variability in its luminosity due to its contracting and heating processes. Powerful stellar winds and intense magnetic activity also characterize this phase. Surrounding the young protostar is a rotating disk of dust, gas, and dust, which is a remnant of the protoplanetary disk from which the star formed. This protostellar disk plays a crucial role in the formation of planets within the solar system. The intense radiation and stellar winds from the young protostar can have feedback effects on the surrounding environment. They can clear out nearby gas and dust, shaping the solar system's initial conditions. The transition from a collapsing region within the pre-solar nebula to a fully fledged protostar typically takes tens of thousands to hundreds of thousands of years, which is relatively short on a cosmic timescale. Once the protostar reaches a stable state, it enters the main sequence phase, where it will remain for most of its life. Our life, for example, is currently in the main sequence phase and has been for about 4.6 billion years. It will remain in this phase for several billion more years before eventually evolving into a red giant and then a white dwarf. The accretion of planetesimals. Within the protoplanetary disk, microscopic dust grains began to collide and stick together due to various forces, including van der Waals force, electrostatic attraction, and the collisions driven by Brownian motion. These processes resulted in the formation of larger dust aggregates. As these aggregates continued to collide and merge, they grew from sub-millimeter sized particles to centimeter sized particles. The gentle spiral motion of gas in the protoplanetary disk played a role in these collisions, facilitating the aggregation of material. The centimeter sized particles eventually collided and stuck together, forming pebble sized and then rock sized objects. These growing aggregates are known as planetesimals. Planetesimals could range in size from a few meters to hundreds of kilometers in diameter. The larger planetesimals had stronger gravitational influences and could accrete material more efficiently. In the crowded environment of the protoplanetary disk, planetesimals also experience gravitational interactions with each other. These interactions could lead to changes in their orbit, including scattering and migration towards or away from the Sun. Within the protoplanetary disk, there was a boundary called the snow line. Beyond this line, water and other volatile compounds could freeze into solid ice. This distinction had significant implications for planetesimal composition, as those inside the snow line were primarily composed of rocky and metallic material, while those beyond it could contain substantial amounts of water and ice. The process of planetesimal formation likely took hundreds of thousands to millions of years, depending on location within the protoplanetary disk and other factors. The formation of protoplanets. As planetesimals continued to collide and merge, some of them grew in size to become much larger bodies known as protoplanets. These protoplanets had sufficient mass and gravity to attract more materials. Protoplanets often migrated within the disk due to gravitational interactions with other planets and the surrounding gas. These interactions could lead to orbital changes, both inward and outward. Protoplanets, particularly the larger ones, had the ability to clear out their orbital paths by gravitationally attracting and absorbing nearby planetesimals. This process is essential for the eventual formation of stable planetary systems. Depending on their location in the protoplanetary disk, some protoplanets became the building blocks for terrestrial planets like Earth, while others accumulated vast amounts of gas to become the cores of gas giants like Jupiter. In most protoplanetary disks, multiple protoplanets formed, each competing for available material. These interactions could result in some protoplanets merging to form larger bodies or being ejected from the solar system altogether. The clearing of debris. The gravitational influence of protoplanets and their continued growth led to the removal of debris, planetesimals, and other objects from their immediate vicinity. This process cleared out the regions around protoplanets, defining their future orbits. While many planetesimals and smaller objects were absorbed or ejected, some residual debris remained in the asteroid belt between Mars and Jupiter, the Kuiper belt beyond Neptune, and the Oort cloud in the distant reaches of the solar system. Formation of terrestrial planets. Terrestrial planets like Earth, Venus, Mars, and Mercury formed in the inner regions of the protoplanetary disk, where temperatures were too high for volatile gases to condense into solid form. Consequently, these planets are primarily composed of dense, rocky material. Within these inner regions, protoplanets grew by accreting solid materials such as silicate-rich planetesimals and smaller objects. Over time, the gravitational attraction to these protoplanets allowed them to accumulate more material. As protoplanets grew in size, their interiors heated up due to the energy released by ongoing impacts and the decay of radioactive isotopes. This heat led to a process called differentiation, where denser materials, e.g., iron and nickel, sank to the core, while lighter silicate materials formed the mantle and eventually the crust, which we'll discuss in greater detail in relation to Earth. During this period of planet formation, there was intense and frequent bombardment by other objects in the solar system. These impacts shaped the surfaces of terrestrial planets and caused extensive melting and resurfacing. Early in their history, terrestrial planets may have had magma oceans, vast seas of molten rock. Over time, these cooled and solidified to form the planet's first crust. The formation of gas giant planets. Gas giant planets like Jupiter and Saturn formed in the outer regions of the protoplanetary disk, where temperatures were cooler, allowing gases like hydrogen and helium to condense into solid form. These gas giants began their formation process with the accretion of solid cores. These cores could have been formed by the accumulation of rock and ice or by the rapid accretion of gas into a smaller protoplanet. Once a solid core reached a critical mass, typically several times the mass of Earth, it had enough gravitational pull to rapidly accrete surrounding hydrogen and helium gas from the protoplanetary disk. This process continued until the gas giants became massive enough to capture and hold significant amounts of gas. Gas giants' immense gravity allowed them to retain their thick atmosphere of hydrogen and helium, making them the largest planets in the solar system. In some cases, gas giants might have experienced orbital migration where gravitational interactions with other planets or the residual gas in the disk caused them to move inwards or outward from their formation locations. The formation of the moon and the Theia impact hypothesis. The formation of the moon is best described by the giant impact hypothesis, often referred to as the Theia impact hypothesis. According to this theory, around 4.5 billion years ago, a Mars sized object named Theia collided with a young Earth. The impact was extremely energetic, leading to the complete or partial vaporization of Theia and significant portions of Earth's mantle. Debris from the impact was ejected into orbit around the Earth. The debris from the impact formed a disk of molten rock and vaporized material around Earth. Over time, this material coalesced and cooled, gradually coming together to form the moon. The moon is primarily composed of material from both Theia and Earth, although it has a higher proportion of Theia-derived material. This is determined by isotopic analysis of lunar samples. The collision with Theia had profound effects on Earth. It may have helped to accelerate the Earth's rotation and contributed to the formation of Earth's tilt and its oceans. After its formation, the moon experienced extensive volcanic activity, meteorite impacts, and geological processes shaping its surface and interior. The evidence of this history can be observed on in the moon's surface features such as craters, mountains, and lava plains. The differentiation of the Earth. Earth's differentiation is the process by which it evolved into distinct layers, each with unique properties and compositions. The innermost layer of Earth is the core, which is primarily composed of iron and nickel. The core is divided into two parts, the solid inner core and the liquid outer core. The inner core is solid due to immense pressure, while the outer core is molten. Surrounding the core is the mantle, which is composed of solid rock, predominantly silicates rich in iron and magnesium. The mantle is partially molten in some regions where convection currents drive the movement of tectonic plates. The outermost layer of the crust, which is composed of solid rock, primarily silicates, it is much thinner than the mantle and is divided into the continental crust, thicker and less dense, and the oceanic crust, which is thinner and denser. Early in its history, Earth was bombarded by numerous planetesimals and protoplanets. The energy generated from these impacts, as well as the heat from radioactive decay of elements like uranium and thorium, caused Earth to heat up. The intense heat led to the formation of global magma ocean, where Earth's surface was covered in a sea of molten rock. As it cooled, minerals began to crystallize, leading to the separation of denser material towards the core and lighter materials towards the Earth. Um, and as I've already said, dense iron and nickel sank to the center of the Earth, forming the core. This process, known as core accretion, released gravitational potential energy and contributed to Earth's internal heat. Less dense silicate materials rose to form the mantle and eventually the crust. These processes also involved differentiation based on chemical composition. Earth's heat is transported through the process of convection. In the mantle, hot, dense material rises while cooler, denser material sinks. This convection flow in the mantle is responsible for plate tectonics, which plays a significant role in shaping Earth's surface. The geological evolution. Earth's outer shell is divided into rigid plates that move and interact along plate boundaries. This process, known as plate tectonics, is responsible for the formation of continents, mountain ranges, ocean basins, earthquakes, and volcanic activity. Over geological time, the movement of tectonic plates can result in a collision of continents, leading to the formation of mountain ranges like the Himalayas. Volcanic activity occurs at plate boundaries and hotspots where molten rock from the mantle, called magma, reaches the surface. This process creates volcanic landforms and contributes to the recycling of Earth's crust. Weathering and erosion processes continually reshape Earth's surface, wearing down mountains and transporting sediments to be deposited in river valleys, deltas, and ocean basins. And eventually, that eroded material will form rock, sedimentary rocks. Changes in Earth's orbit, axial tilt, and greenhouse gas concentrations have led to fluctuations in the Earth's climate over geological timescales, resulting in ice ages and warmer periods. Earth's oceans formed as water vapor in the early atmosphere, condensed, and accumulated in low lying areas on the surface. Oceans played a crucial role in the development and sustainability of life, which we'll see in upcoming episodes. So I hope you liked the episode. Hope you found it as fascinating as I have found it. If you did like it, hit that like button on YouTube, or uh, I don't know what you do on Spotify. Leave a comment, uh, write a question, and Also, you could subscribe both on YouTube or on Spotify. Anyway, hopefully you, like I said, hopefully you enjoyed that. I'm going to leave it there. I'm New Minus 72. Wherever you are in the world, in the evening, evening, afternoon, morning, have a great day. See you later and take care. Bye for now.